Hey, so let's talk about some momentum here, okay? What I want to do is I'm going to do this series of videos for you, and kind of basically I'm going to cover these things that you see below there: types of collisions, quantity of motion. We'll do all that here in this first video, and then I've got about 4 other videos that I'll do for you where I illustrate different ideas and some examples of how we actually put numbers to paper and get some answers so that we could predict behavior or understand what's happened in different scenarios. All right. Um, I really like old pictures, and this is actually one of my favorites. So if you want to try to figure out what is that's going on in that picture, and I'll come back to that later on in a different video and tell you what is actually happening in this particular picture here. But it's it's hilarious. Okay, so moving right along here, then from your soft chalks, we can talk about 3 basic kinds of collisions, okay? And the first collision is really we would consider to be an explosion, all right? And so anytime we have an explosion, then we're dealing with a situation where the total momentum of the situation is going to be 0, okay? Now, momentum is a vector quantity, all right? So we always need to sort of specify what direction we're talking about. In more advanced coursework, okay, you might have to deal with the momentum in the x direction and the momentum in the y direction, okay? Now, in this course right here, right now, we won't be doing that, okay? But some of you will be taking dynamics in the spring with me, and we will do a little bit of that there. But in the case of an explosion where we have just one-dimensional behavior here, if we label these things, maybe call it this one 1 and this one 2, all right, what we're going to end up having is M1 V1 plus M2 V2 is going to have to be equal to 0. Okay, and so then that becomes our defining relationship for how to relate what's happening with particle 1 to what's happening with particle 2. For the next 2 situations where we have some kind of an elastic collision, okay, then when we conserve momentum, it's a little bit different. Okay, and again, we're going to limit ourselves to just x momentum here. But now we say that the initial momentum is equal to the final momentum like this. And so again, let's call this 1 and this guy 2. And then we've got a before and an after. So we have an initial and we've got a final state. So in our initial state, what we would say is we would say M1 V1 initial plus M2 V2 initial has to be equal to M1 V1 final plus M2 V2 final, just like that. Okay, and that's going to be true both in the elastic sense and in the perfectly elastic collision below. Okay, now let's suppose that I knew how fast V1 initially was going and V2 initially was going and V1 was going in the end. All right, so I have one equation, and as you can see right there, then I have one unknown, and so that's easily solvable. Okay, so we've got four bits of information regarding velocity. If you give me 3 out of those 4, then I can tell you the missing piece. Okay, but what if we didn't know anything about the final situation? Okay, so if we only know the initial 2 velocities, then that equation that we've got right there is not sufficient to get all the information that we need. Okay, so we need another piece of information, and that has to do with the elasticity. Okay, and really what we would call the restitution of the collision. Okay, and that works like this. So we would say delta V final is minus epsilon naught is what that is. Delta V initial. Okay. Now, when I'm writing this as delta V final and delta V initial, what I really mean here is something like this. V1 final minus V2 final is equal to minus epsilon naught V1 initial minus V2 initial. Okay. And as long as we are consistent, left, right, right, it doesn't really matter which way you do it. You just got to be consistent. So you could do V2F minus V1F equals minus epsilon naught V2I minus V1I. That doesn't really matter. That's just a minus sign in our whole equation. Just be consistent and it's fine. But what I want to point out now is between my two equations, this one and this one, the one on the top. So maybe I know everything that's happening initially. Now look at this. Okay, now I don't know this guy. I don't know this guy. This guy. There we go. So now I've got two equations and two unknowns, and so I can work that out. Okay. And obviously some of you figured out that I forgot a sticky collision here in my diagram. Sticky collisions are really, really straightforward to deal with. So we're going to have one object and it's going to collide with another object. They may or may not be moving. It better be moving slower or they're not going to stick. They're not going to clash. And so that's our before picture. And our after picture, they're like stuck together somehow, moving with a common velocity. So in that case, P initial is equal to P final, just like we've been talking about. But what we're gonna say is we're gonna say M1 V1 initial plus M2 V2 initial has to be equal to the total mass M1 plus M2 and some velocity, which I usually like to put it together, call it V12, something like that. Okay. And again, in that last equation there, I'm going to have to know 2 out of 3 of those bits of information, okay, in order to get that. Okay, so let's look at a couple of super simple scenarios. All right, in the first case, we've got a pickup traveling at a certain speed. What's the momentum of the pickup? All right, now these are really, really simple. And the reason for doing them for you is so you can begin to understand the recipe for how we approach these, okay? So if you can understand the recipe on a really simple problem, then you can understand it, for something more complicated, all right? So what we want to do is we're going to draw. So I'm going to do this first one with the pickup first. So I'm just going to make it abstract, okay? So I got a pickup, got a certain velocity here, just like that. And I want to put a lot of information on my sketch, like we always do. So my mass is 800. It's just my sketch. I'm not going to worry about units or sig figs. I've got this right there. Okay, and what we're interested in finding is what's the momentum of that thing. Okay, and so the momentum there is just mv. Okay, we don't have a before and after this time. I'll show you how we deal with that in the videos that are on the way. Okay, and so we're going to end up here with 800 onto 30. Oops. I forgot my units. Uh-oh, -1 point. Okay, there we go. So we got 30 meters per second. Okay, and it's a pretty big 800 times 30. This is 24,000. Okay, now check out these units. There's no way around it. These are just kind of ugly. Kilogram meter per second. That's what we're stuck with our units for momentum. It is not pretty. Okay, kilogram meter per second. There's no nothing like if we had a kilogram meter per second squared, that's a Newton. Okay, that's a unit of force. But for our kilogram meter per second, we don't have any fun little thing like that. So okay. Anyway, so now the next one says What speed would Freddie the Wonder Cat have to run in order to have the same momentum as the pickup? Okay, so again, what we'll do here is we're just going to represent Freddie as an object. Freddie's mass is 5. And in this case, we don't know the velocity, but we know the momentum has to be 24,000. Okay. And so if we work all this out, okay, we get mv. Do a little algebra. V is p over m. And put our numbers in. 24,000 kilogram meters per second over 5 kilograms. See what happens with our units. We lose the kilograms. We're left with meters per second. So that works out pretty nice. And what we get when you run that on your calculator is 4,800 meters per second. 4,800 meters per second. So that is one badass kitty, let me tell you what. That's approximately, I worked it out, that's approximately 14 times the speed of sound. So, yeah, it would be fun then to kind of maybe figure out, okay, what's the friction effect and how hot does Freddie get? And then we could calculate how much time would it take for Freddie to, in fact, incinerate himself. Sorry. Okay, I'm cracking myself up. All right, so I got some more examples coming for you, but this is the sort of the basic idea. You're going to see this pattern over and over again. We're going to make a sketch. We're going to put lots of information on the sketch, and then we're going to start with a momentum equation, and then we'll work it from there, okay?